Hi, welcome to Functional Justin episode 13. So if you're new to the series, you might want to skip back a couple of episodes just to catch up. What I talk about on this channel is functional programming, and what I've been looking at is Scala 3 and using Scala 3 to build up a category theory library of monads like the reader T and the writer T. And in this episode, what I'm going to talk about is what happens when you want to combine monadic effects. So just to back up a little bit, what we've been doing throughout this series is looking at a simple program that evaluates an expression, and we have been building up our repertoire of monads to add effects to that program. So we used either to handle errors. We showed how you can use the writer T monad transformer along with the either monad to handle errors, and also to write a log of the computation as it progresses. And another thing we looked at was using the reader T monad transformer. So you can write programs with effects that have a read-only environment. So writer is for logging and reader is for a read-only environment. So the obvious question is, what if I have an effectful program and I want to add multiple capabilities? So a good example would be taking our program and adding the reader and the writer at the same time. So fortunately, that's perfectly possible. If you think about the way that reader T and writer T are defined, both of them take a monad as their first type argument. So if you take the reader T or the writer T, that first monad can be a monad transformer itself. So if you look at the type signature here, we've got the writer T, and then the first parameter is going to be the reader T, and then as normal we have the log type and the result type all there as well. Alright, so let's take a look at the code and then we'll take it from there. Our starting point is the expression evaluator program, and we're adding capabilities to that program using different kinds of effects. So we start with some expression of all of the different kinds of operation we support, and for each of these expression types there's going to be an implementation, and you can see that in this eval function that we're just going to call the appropriate we're doing a pattern match on each element of the expression, and each of those is going to do something, and then the actual details of the program we sort of delegate out to the type system using all kinds of different effects. So we've done reader T, we've done writer T, so you can skip back a couple of videos to watch those in detail. And I'm not going to actually code this right now, I'm just going to show you the end result. But what I did is, just like in the diagram, or just like in the slides before, I showed you how writer and reader can nest each other. That's literally what I've done here. So we take the expression and we're going to pass it into the program using reader T's run method. We're also going to use the writer monad's unwrap method. So essentially we're going to run the program and then we're going to unwrap it, which will give us the reader monad inside, and then we're going to run it with the environment, with the symbol table. So already the ergonomics are a little bit, I would say, not quite as nice, because we have to deal with this double layer of nesting. Anyway, so we take our program, and then the result of this, you can see, is either an error, or it's going to be a tuple of list of strings, which is our log, and the final result. So when you run this, you can see that I print the result out, which is the second element of the tuple, and then I print the log, and I'm going to reverse the log just because the log is built backwards essentially. So what we can see is that when the expression was evaluated, we can print out the order that everything happened. So that's nice, and so we're using the reader monad and the writer monad. So let's take a look at what that did to our code. So essentially all I had to do was make a new type for the expressions and then fix all the type errors, and there was not a lot of implementation to do. So let's take a look at the simplest operation, the val method, which just takes a pure value. So to make a pure value, we have to do a bunch of work. We have to, first of all, use the reader T's lift method to take an either value. So here's our log. Right, so essentially our writer t is going to contain a reader of an either, and the value here is the log value and then the result value. So there's a lot of stuff going on there, even though this is our simplest case. Now what we could do is also use the writer t lift method there, and then call the tell method on it. That would probably be more idiomatic, but this works fine. The next most complicated thing is to implement the variable lookup. So this is something that takes a string and returns the value from the symbol table. So let's take a look. So the input to handle var is just the name of the symbol, so that's a string, and then the type of all of our expressions has this same type, so it's the writer t with a reader t nested inside that, with an either inside of that, and yeah. So first of all, we have to let's take a look at what we're doing. So here's the thing that's doing the actual work of getting the symbol from the symbol table, and it gets the symbol table itself from the reader t environment, which remember we're going to pass that in when we call the function. And if it finds it, then it returns a write value with the log and the actual value. And you can see here that we're just logging what we did and then adding the value to it. And if there's an error, then we just return a left. Once we've created the reader t, then we wrap it in a writer t, and that's all we need to do. The next thing we need to do is all of these expressions, add, subtract, divide, multiply. We have to add this new massive type signature, and then we have to implement an extension method for numeric so that we can do plus, minus, multiply, divide, just given a numeric of the right type. So let's take a look at that. So here's our extension method. Because the type signature is so big, Scala had real trouble if I use aliases to simplify things. So this is why you can see these really long lines where I've written these types out, and it's really the only way to make everything work correctly. Another problem I had was that I'm just going to comment this out for a second, and this is the simplest way to implement the addition, right? All we need is we have an applicative instance for writer t and reader t, so that means to do addition, this is all you need. Now I should be able to write it just like this. Which is what I did in the other videos, but you'll see there's no instance there, and this is because Scala can't find this extension method, and that's because our type is just getting so complicated. Now it might be possible there are techniques to make this work, but I just bring in the monad I need explicitly like this, and then I can use it explicitly. So that solves the problem, but really things get a little bit hairy once you start to nest your monads, you know, in multiple ways. Everything gets a lot more difficult. Alright, let me just uncomment that. Okay, so you might be wondering what this map_tell function is. So one of my other videos I went into this technique in more detail. The idea of map_tell2 is really just a helper function, and what it does is it lets me explicitly write a function that takes two writer t's, so that's the fa here and the fb there, and a function that maps a tuple of a and b to a c, and this other function that maps the log of a and b and a result to a log. So there's a lot going on there in the type signature. But essentially what this lets you do is take two expressions of type writer t, and I want to be able to get the input parameter, the output parameter, and also the result, and I want to be able to pass those to the logging function. So that lets me write a more interesting log of this happened, here are the inputs and here are the outputs. So in other words, it gives you a way to expose the logging function to the actual operation that you're doing. And so you can see that the way that works is it unwraps both the monads, it runs the function on them to get the result, and then it runs the function to get the log, and then it combines the logs with the previous logs, and then it wraps them all up in a writer t. So what that really does is just let me simplify my code here. So when I'm going to do addition, say, I call maptel2, I pass in the left hand side and the right hand side of the expression, and then I have one function that calculates the result. In this case it's simple addition, and then another side that calculates the log. So this is one way to do logging that I find quite convenient. Another way to do it is to embed your logging in a flat map. That's what I'll do with the Zio Prelude later on. It's a slightly different way of doing it. But anyway, just to explain what's going on. So anyway, the conclusion here is that you can nest monad transformers to any depth you want, but as you add depth, it doesn't scale very well. So in terms of type complexity, in terms of readability, in terms of programmer ergonomics, it's really not a great experience. So the idea of ZPure is it's a monad that does everything, or not everything, but it has all of the effects that you might want to use. So for example, if you look at the type signature here, it actually has 6 different type signatures, and what we've done is, or what the Zio people have done, is rotate the parameters. So instead of being a vertical stack of monads that each requires its own data structure, it's a single data structure with 6 parameters. So if you visually think of it rotating 90 degrees, and this is referred to as effect rotation, and then you can write an interpreter which builds up a data structure of ZPures and then evaluates them all at once. So you can imagine there's all kinds of efficiencies that you can build into this that you can't build into a stack of data structures. So taking the type parameters one at a time, we've got W, which is the log type. We've got S1 and S2, which can hold mutable state, and it represents state both before and after a computation. We're not going to be using that in this video. R is the environment, so that's the reader monad essentially. E is a channel for errors, so we will be using that one. That will be what we were doing with either. And then A is the successful return value. So from their own documentation, ZPure can model a variety of effects, including context, state, failure, and logging. So let's take the parameters one by one. So the W parameter is string, so we're going to log a sequence of strings with this computation. The next 2 parameters are any, which means that we don't want to constrain them. We're not going to be using state, but someone else could use a program and they can inject some state later, but we're not going to do it right now. The 4th parameter is the reader parameter. So just like in our previous program, we're using a symbol table, so a map of strings to integers, and I've used a type alias, so that's what env is. Error is my custom error type, so this is a sealed trait that represents all the different kinds of errors that this program can return. And then finally we've got A, which is just the computation return type, which in our case is going to be a numeric of type A. So that's what ZPure looks like. Now let's look at how we can implement it in code. Do the same program again, but without monad transformers. We're going to use Zio Prelude and the ZPure data type to make everything work. So our starting point is essentially the program, and I've stripped out all of the monad stuff, and I brought in the Prelude and got rid of the standard library numeric and brought in my own. And I'm not using Scala 3 for this. I think when I started this project, Prelude wasn't compiling for Scala 3, so I did write the code in using Scala 2. So you'll notice that this is using the let's call it the old-fashioned type class formulation, not the new one that you'd see in Scala 3. But really, Scala 2, Scala 3 doesn't make much difference for the sake of understanding how ZPure is going to help us here. So anyway, here's our error type. So that's just a sealed trait of different kinds of errors. Our log type is just a string. Our env type is a symbol table. Here's our ADT of different operations that we're going to support. Now here's the important part. Here's the new return type for our functions, which is now going to use ZPure. So there we just pass in all the parameter types that we're interested in, and then we can take our program, we can change the return type of everything, and then all we need to do is fill in the missing implementations so that we can see how ZPure works. So let's start with the easiest one. So the easiest one is to handle our literal values. So what we're going to do is create a ZPure effect with the succeed method. Now succeed lets you take a pure value and create a ZPure. So this is similar to the pure function that we've already seen from category theory, taking a pure value and lifting it into an effect. In Zio and Prelude, some of the category theory names have been replaced with more familiar names, more English names. So this is why it's succeed and not pure. So we can just take succeed and succeed with the value, and that will sort of work. So you can see that our test expression here is just a value 10. So with that bare bones implementation, we can now run the program, and you can see that the output is a chunk, which is what our log is coming back as, and then we have an either, which contains a tuple of the return value, which is 10, and unit, which is our error. So in other words, there's no error. So when we run it, you can see that the return value is chunk, which is the data type used to represent the log, and then we have an either, which gives us either a left and the error, or what we got, which is this tuple of unit and 10. So 10 is the actual return value of the expression. So remember, it's just a literal value 10, and the unit is state. Now we're not using state, so unit is just what we got back as a default. And then we printed all of the log values, but that didn't print anything because we don't have any log yet. So what we can do is start to build out a log. So what we would do in this case is we can say, we can take a ZPure, we can call log on it to add a new log entry, and we can say it's a literal value and the value is value. So now we can run it, and now you can see that as well as a return, we also got the first line of the log. So the next thing we'll implement is variable lookup. So if I was to run this with expression 3, we should find that it will fail because we didn't implement that yet. And when we run it, you'll see, boom, implementation is missing. So we have to implement the handle variable function. So how does handle variable work? Well, it has to take the environment, which is what we used to have in the reader T, has to be able to look up a symbol given a string, and has to be able to handle the error that the symbol is missing. So to access the environment, we use ZPure's environment method, and this has two types. First of all, it has the state type. We're not using state, so we just ignore it. And then we can pass in our reader type, which is going to be env of type A, and that gives us a ZPure effect. And when we flat map that, that actually gives us the an environment that we can work with for our computation. And the next step is to look inside that and get an option of whether the symbol exists or not. So we can do env get s, and that's an option, but we really want it to be a ZPure. So we can use the ZPure method from option, which turns that option into a ZPure. But it's still not the right ZPure, because remember that we have a specific error type. So what we want to do is whatever the error is that we got here, you can see that the error type is unit, right? And we need the error type to be the error that we defined. So now we can use the map error function, which is a function that lets you take a ZPure and run a function on it, so that if there is something in the error channel, you can transform that value. And what we want to do is whatever it is, well, we know what it is, it's either unit or it's not an error. We want to just turn it into our symbol not found error. So that's a good implementation, and I think you'll find that that will run. And you can see our return value is 1. we don't have a log yet. Now, this is a bit more tricky to write a log than the literal value, because we want to be able to see the value to print a useful log about it. So in the literal value, we knew what the value was because it was passed in. We don't know what the symbol is in the symbol table until we actually looked it up here. So what I'm going to do is to flat map that thing, the effect that we've got so far, and that will give us the A. So that's going to be the value that we actually got out of the symbol table. Then I want to create a new ZPure effect, and I'm going to add a log to it. And that log is going to be that we got a variable, and its name was S, so that's the thing we passed in, and its value is going to be the A here that came into this flat map. And you can see that the type is wrong here, and the type is wrong because we just created a ZPure log, but what we really want to do is convert it to something of type A. So if we were to do as A, that converts everything to the right type. So that's all we need to do to get logging working. So now you can see that my output is that we looked up the variable x and we got the value 1, right? So everything is working, and you can see that chunk now is starting to be populated with the step-by-step of the expressions. So the next thing we need to do is to get the whole expression working. That means we need to implement add, multiply, and subtract, and divide, and then we'll be able to evaluate that whole expression there. So let's use expression 1, and now I have to implement the missing pieces. So the easiest way to implement this would be to use ZPure's zip operation. So I can take any ZPure and zip it with another one. So what that gives me is the values of x and y, in other words the left and right hands of the expression, and then I can flat map those and execute whatever function I need to do. So this is going to give us the two sides A and B, and then I can simply add them together. Right, so that's the simplest implementation we could do, but this doesn't help with our logging. So I want to do some interesting logging. So instead, I'm going to flat map them again, and then I need to create a ZPure which has the successful value and also the log value. So I can succeed that, and the successful value is going to be the sum of the two things in this case, because this is the add operator. So we get a successful ZPure, and then I want to create the log entry. So this is going to be that we added A and B and got actually I don't want to repeat myself, so let's do this. And this should be C. Alright, so that's what we need to do to add things. And then multiply is going to be like this. Subtract, this is going to be A minus B. Subtract, now this is actually reversed, so we want to say that we subtracted B from A and got C. And then finally divide. Divide A by B. And that's it. So I think you can see that the code is a lot cleaner, a lot easier to read, a lot easier to develop, and I think it's actually quite a lot more efficient because we're creating a lot less data and poking inside classes because we don't have this big nesting of classes anymore. So I haven't done any benchmarks, but I plan to do some benchmarks in the future, see what the differences are in terms of not just the amount of classes that are created, but also in terms of the speed and performance. Alright, so we can run this now. And there you go, we can see that we have a log of the whole computation. It's in reverse order of the operations, because that's the way the log was built. And then at the end you can see that we added 100 to 100 and got 200. So that's it. So you can see that ZPure really scales well. If I was to add more state, more readers, I can put them all essentially in the same slot, and I think you can really see that composition comes into its own when you're using ZPure. Okay, that's all for this video. Not sure what the next video will be. I'm probably going to do these videos once a month from now on instead of every 2 weeks, just because I'm busy with my day job. But hope you enjoy it. Please like the video, please subscribe, and thanks very much. Bye now.